In our everyday experience, the universe behaves like a rigid, three-dimensional grid. You can measure a room with a ruler and time an event with a clock, confident that a second for you is exactly a second for anyone else. This intuitive view is backed by classical mechanics. If you are on a train moving 50 miles per hour and you run forward at 10 miles per hour, an observer standing on the ground measures your total speed as 60 miles per hour. But light refuses to obey this math. The speed of light in a vacuum is a constant 299,792,458 meters per second. It does not matter if you are standing still or hurtling through space. You will always measure light moving at that exact speed. This creates a mathematical paradox. If you stand on that same 50-mile-per-hour train and shine a flashlight forward, the light does not travel at its usual speed plus 50 miles per hour. It just travels at the speed of light. The velocities do not add up. To keep the speed of light perfectly constant across all measurements, the rigid grid of classical physics has to break. Space and time cannot be independent fixed stages. They are a single, flexible fabric, space-time. Let's test this flexibility with a thought experiment involving two observers. One is a passenger inside a fast-moving train car, and the other is a bystander standing still on the station platform. This 2D cutaway shows the passenger's perspective. If a light pulse drops, it travels in a straight, vertical line. But the platform bystander measures something different. Because the train moves forward, that exact same pulse traces a longer diagonal path. Speed is simply distance divided by time. Both observers must agree on the speed of light, but they disagree on the distance it traveled. The only way the math holds up is if less time passes for the passenger. The passenger's clock is physically ticking slower. Time dilation alone isn't enough to balance the equation. Along the direction of travel, the physical dimensions of the train car must also contract, shrinking the distance the light has to travel from the perspective of the platform. Space compresses and time stretches to keep the speed of light absolute. This is the core of special relativity, but it only applies to inertial frames, objects moving at a steady, unchanging velocity. The actual universe is rarely that neat. Massive planets orbit, powerful rockets launch, and objects fall. We inhabit a universe defined by acceleration and gravity, which required a new framework to map onto flexible spacetime. Picture yourself inside a sealed elevator car like this one, with no windows to the outside. If you hold an apple and let go, you watch it drop to the floor, accelerating at 9.8 meters per second squared. Here is the problem. Based solely on the behavior of that apple, are you resting on the surface of the Earth? Or are you floating in deep, empty space inside a box, being propelled upward by a rocket at exactly 9.8 meters per second squared? Einstein realized that there is absolutely no physical measurement you can perform inside that sealed box to tell the difference. Gravity and uniform acceleration produce the exact same observable results. Because they are indistinguishable, they must be physically equivalent. This means gravity cannot be a traditional pulling force acting invisibly across vast distances. Imagine the elevator cable snaps. You are now in freefall. If you let go of that apple, it doesn't fall to the floor. It floats weightlessly right next to you. In classical physics, you are being pulled toward the ground, but relativistically, you are experiencing the opposite. Without the floor pushing up against you, you are in a natural state of rest. Freefall is inertial motion. If free-falling objects are just moving in straight lines at natural rest, we hit another paradox. If you drop an apple over New York and someone drops an apple over Tokyo, they both fall straight down. Yet if they could fall through the Earth, those two perfectly straight parallel paths would eventually cross. This 3D animated diagram shows why. Massive objects warp the geometry of the space-time grid around them. Those two apples are traveling in straight lines, but because the grid itself is curved toward a dense center, the straight lines naturally converge. This is general relativity. Gravity is geometry. The presence of mass tells space-time how to curve, and the resulting curves of space-time tell mass how to move. Zooming out to the scale of the solar system, the Earth isn't being swung around the Sun by an invisible gravitational tether. Our planet is simply gliding forward in a straight line, along a deeply curved space-time valley created by the Sun's mass. These relativistic effects create hard engineering constraints that dictate the performance of our most advanced technology. Consider the global positioning system. The infrastructure that enables global navigation relies on a constellation of satellites, and those satellites require extreme precision to function. At 14,000 miles per hour, special relativity causes satellite clocks to tick 7 microseconds slower per day than Earth clocks, but orbiting 12,000 miles high in weaker spacetime makes them tick 45 microseconds faster. Engineers must offset this difference, or global navigation fails. Our common sense view of the world is a convenient, localized illusion. The reality we inhabit is a beautifully warped fabric, governed by the unified laws Einstein spent a lifetime uncovering.